Differences between polyprotic and the monoprotic is that if you dissolve the substance inside the water, it can actually generate more than one proton. In chapter 13, those are the biprotic acid that you need to know. There's only one triprotic acid. So most of the time, it's actually very straightforward. For the acid, you can't see how many protons you have. One exception is actually this guy. That's the things that you want to actually memorize. H3PO2, H3PO3, H3PO4. These are the sets that can get you confused. There is actually the monoprotic, there's a biprotic, there's a triprotic. What we're going to do today is actually to tell you how you can actually handle a problem like this. If an acid can actually dissociate and generate more than one protons. Okay, how are you going to calculate the pH? So for the H2SO4 itself is actually a biprotic acid. So what you're going to do is actually H2SO4 is going to dissociate, generate proton plus HSO4 minus. What's going to happen later is that HSO4 minus can further dissociate and generate another proton, and then SO4 2 minus. The percent dissociation will be very different because the Ka1 for your H2SO4 is around 10 to the second power, but the Ka2 is only 10 to the negative 2 power. So we say the Ka is actually a parameter you can use to judge how strong your acid is, right? The larger the Ka, the stronger the acid it will be. Okay, so if you look at these two equations, which equation will generate more protons? First one, right? Much higher number, right? It's actually 10 to the fourth power, larger than the second one. In other words, for this biprotic acid, your proton source is mainly contributed from your equation 1. Okay, even though I write two equations, right? Majority of your proton comes from your equation 1. So you know the major ionic species in this set of equation will be proton, of course, is 1, right? Your HSO4 minus will be the major species. And this is mainly all coming from your equation 1. For your minor species, it will be your SO4, 2 minus. Okay, so how do you calculate proton concentration in this case? For the first step, because your Ka is actually big, we assume it's actually 100% dissociation. Okay, whatever concentration you have here, it will give you that much proton concentration and that much HSO4 minus. From the first step, you know how much proton you can generate, and then how much SSO4 minus you can generate. In the second step, this guy can further generate another protons, right? So this one apparently is actually a weak acid. In the second step, you still generate certain portion of H+. So what you do is actually you know the concentration of this guy, then use your ice table to solve the proton concentration afterwards. Then you add up the proton concentration in two reactions. They will be your final proton concentration. Okay, then you can calculate your pH from there. If you do the same analysis for the triprotic acid, this is probably the most complete case you are going to see in this chapter. H3PO4, you should know it is like a triprotic acid. It will dissociate, generate H plus and H2PO4 minus with a Ka1 roughly 10 to the negative 2. H2PO4 minus can also generate protons and then forms the HPO4 2 minus with a Ka of 10 to the negative 7. This guy can further dissociate, okay? HPO4 2 minus, that become H plus PO4 3 minus with your Ka3 10 to the negative 11. So what will be the major species in your reaction? H2PO4 minus, right? So this will be actually the dominant species inside your solution. And it's so dominant because you can see that the difference between each step is actually 10 to the 5th and 10 to the 4th, right? Every single step, it got weakened significantly, right? Therefore, the proton it can generate in the second and the third step is basically negligible. So later on, you will see an example. You'll find out that the proton concentration for this polyprotic acid mainly coming from your first step. So the minus species here will be your HPO4 2 minus and the PO4 3 minus. If not, let's go through one examples so you can see the things better. So here it says calculate concentration at equilibrium of H2CO3, HCO3 minus, CO2 2 minus, and proton concentration, where we know the initial concentration of your H2CO3 is 0.03 N, and the K1A and K2A is certain number. Multiple keyword here, okay? So the first thing I noticed actually you have 2Ka, right? Means it's actually a biprotic acid. So those are the features you want to pay attention to. 2Ka is biprotic acid. So you just start to write the things out, right? You know you have H2CO3. Dissociate become H plus and the HCO3 minus, where your Ka1 is equals to 4.3 times 10 to the negative 7. And then you have HCO3 minus forming H plus and then CO3 2 minus, with your Ka2 equals to 4.8 times 10 to the negative 11. Can you do these things yourself? Can you translate from the questions to these two simple equations? Okay, then you want to actually calculate the concentrations, right? And then if you the initial concentration of this guy is that much, right? Once you see that, you can actually use the ice table to make it more clear for you. Starting from the first equation, you know initial concentration of your H2CO3 is certain number that's provided inside your questions, right? So here, because it's initial, right? We say you haven't have any dissociation, so we put 0, 0 on your H plus and the HCO minus. And then change is going to happen. Some of them is going to start to dissociate. Okay, that's going to produce XM of your H plus and the XM of your HCO minus. For the monoprotic acid, that's pretty much all you do, right? You're just adding up, then you use your Ka to solve for your X. Here, it needs to be, it's not done yet because you know this guy, which is this guy, is going to do something else, right? So once you formula, you know, in the second step, originally you have that much in the beginning, right? You don't have this yet, but you know, it will further dissociate. So let's say it dissociates by a certain amount called Y, then this is going to produce Y amount of H plus and the Y amount of CO3, 2 minus. And then after all the things are done, then your system will reach equilibrium. So once you reach equilibrium, you know this will be simply Y for your CO3, 2 minus, right? For your proton, right now you have two contributions. One is from here, one is from there. So in the end, what you have is actually X plus Y, X plus Y for your H plus. The same concept applied to your HCO3 minus, because here you know you have X, here you actually have minus Y, right? So in the end, what you have is actually X minus Y, X minus Y for your HCO3 minus. And then for your H2CO3 will be 0.034 minus X. So up to this point, you have everything at equilibrium. So once you have this, then use Ka, right? So you know your Ka1 is going to equals to x plus y, x minus y, divided by 0.034 minus x. And then if you look at the equilibrium constant, it's 4.3 times 10 to the negative 7, right? Can you use small x approximation? Yes, right? So you know this can be rewritten as 0.034. The y will be actually a small numbers. So on the top become x squared. And then this is going to equals to 4.3 times 10 to the negative 7. Therefore, we know x squared is going to equals to 0.034 times 4.3 times 10 to the negative 7. Then you can take the square root on both sides. You can get the answer of 1.2 times 10 to the negative 4. You can do the same thing for your Ka2, right? Because now you know your Ka2 is going to equals to x plus y multiply y divided by x minus y. What is the value of Ka2? You should see that it's 4.8 times 10 to the negative 11, right? Can we use small x approximation here? Yes, right? So you know your y will be actually extremely small. Okay, therefore these things can be rewritten as x times y divided by x, right? So x cancel out. Then you can just solve for your y. So you know your y is going to equals to 4.8 times 10 to the negative 11. Because your x is way bigger than your y. So your x plus y or x minus y, you will basically the same as your x. With that concept, okay, you know x is equals to x plus y, right? Because the small x approximation. So you know this is going to give you the proton concentration, right? So at the end of the day, you know it's actually a weak acid, right? So in the previous sections, we say if you have a weak acid for monoprotic acid, you can calculate proton concentration simply by doing your original acid concentration multiply your Ka, right? You do the same calculation. You know it's actually a weak acid in the very beginning. Then the proton concentration is actually the same equation you calculate for the monoprotic acid. Original acid concentration times your Ka1, take the square root of that and give you proton concentration. The things that you cannot know using our own knowledge is actually that the concentration of this guy is actually you don't know. And then from our calculation here, what it shows you that the concentration of that was simply equals to your Ka2. Okay, so what do we learn from all these calculations is that if today you have a weak biprotic acid, then the proton concentration is equals to the square root of your original acid concentration times your Ka1. Okay, it's less simple. That's the thing you need to memorize. Then you don't need to do all this ice table. The concentration of your conjugate base in the second step is what just equals to your Ka2. Okay, and that's all the things you need to actually memorize.